only?
No, there's a zero right there,
You said the
because there's
direction?
no,
I'm saying it's not moving at that point, at
Yeah.
that peak, it stops moving.
Yeah, it stops moving vertically.
But that point is gonna start moving this way? Is that what happened out there in the hallway? Did those coils start moving closer to Ronald?
Yeah.
Then how did I still have some in my, have still a coil in my hand?
Not the coil, the wave.
Yeah, I'm talking about the point on the, I'm
Oh,
talking,
okay.
not talking about the wave right here, I'm talking about that point on the rope, or coil, whatever it happens to be.
There's some tension in there.
Okay, which way is the tension acting on this spot?
Opposite of what? Opposite of the arrow.
So I got a tension acting that way?
Yes.
What other forces are acting on it?
you got,
Tension in the upper direction.
Like that? Is that what you're going with?
I guess.
and then you got tension, gravity tension too.
There is a gravitational pull here. When we were out in the hallway, because we were going sideways on it, the gravitational pull was being met by normal force from the floor. So let's assume that the gravitational force is minimal compared to the actual tension in the rope. Especially because this should also work in space, or, well, there's still a gravitational pull in space, but it should work regardless of what the gravitational pull is. Assuming that we have enough tension in there to overwhelm it, like we did in the hallway. If those are the only two forces of any significance, the two tensions right there. So if I did a close-up of it, so the way that I heard Nick describing it like this. Did I characterize it?
Yeah,
Okay.
something like that.
We know it's not going to accelerate left or right because the particles of the coil are just moving perpendicular to the transverse to the wave. So if it's not going to be moving left or right, because it started out along this path right here, and it's not going to move left or right, what can you tell me about these two forces?
They're in equilibrium.
If it's in equilibrium and it stops, so at that point right there, it stops. If it's in equilibrium, what's going to happen to it?
It's gonna stay there?
It's going to what?
Stay
Yeah,
there?
it would stay there. And we know it doesn't.
So there's force acting up and down as well.
It's actually, you were really close. Just slightly down.
Ah, dang.
It is the tension, but the tension is not perfectly level. There is a small little angle there. We're looking at some little segment of rope here, not a single spot, a really tiny spot, a tiny section of rope of some mass M.
So it follows the coil, like, it's slightly pointed down, so it would follow the,
Right.
yeah,
Yeah.
it would follow the rope.
Yes. To sort of exaggerate it slightly, if I were looking at that small segment of a slightly larger segment, we have a tension here and here. Looking at it. As I make it smaller and smaller, those two little bits get closer and closer to perfectly horizontal, but never quite there, unless this piece became infinitesimally small. Or actually became completely small, became two-dimensional. So looking at the exaggerated one, I basically have a part of an arc here, a part of a circle, so if I'm part of a circle, I should have a center of a circle right there. And there's some angle here, which we will label phi. And so the question is, if this angle here is phi, so the angle as drawn here, what is this angle right here? I do know that that is a right angle.
Wouldn't that be the same angle as phi?
Yes, it is. So I have these two forces which are sort of acting just slightly below horizontal. If my angle here is phi and my tension here is F sub t, Then the part, draw that triangle a little bit bigger. That's phi. I have tension here. I'm breaking it into components, flashback to physics 131, or trig. What is the length of this side? If I know my hypotenuse and my angle, what is this side?
Are you talking about like opposite? Are you talking about like the opposite adjacent stuff?
Yeah, that's stuff.
That's the opposite, right?
Actually,
That one
no,
right, this one right here would be the adjacent one
Oh, okay.
to phi.
it would
Opposite's
be
the one, picture you're in a
Yeah.
room
Yeah,
with three
yeah.
sides, opposite's the one that,
Yeah.
away from you.
It would be cosine phi equals the adjacent over the hypotenuse.
All right, we'll just call that A and B. So the cosine of phi is equal to A over the tension. So A, this side right here would be the hypotenuse, multiplying both sides by the tension, times the cosine of phi. And what is B equal to?
That'll be the sine.
It would be,
The full thing?
it would be.
Sine times phi equals opposite over FT.
Okay, and what does that come out to?
I was saying it was gonna be, sine phi is equal to B over FT cosine phi. Because
With
A
phi.
equals FT cosine phi.
What is sine anyway? Which two sides am I dividing?
Opposite.
Opposite.
Yeah, so sine is opposite over hypotenuse.
Oh, I'm,
So what does B equal?
B equals, FT.
I was thinking of
sine
tangent,
phi.
I'm sorry.
Yeah.
I'm sorry, I was thinking of tangent.
Yeah, that's a different one. All right. So if I doing my force diagram here of that point, so I've got my bit of mass right here. I've got, however you want to draw it. I've got this sideways component of tension times the cosine of phi going this way, and I have Ft sine phi going down. Over here, I have Ft cosine phi going to the right, and Ft sine phi going down. But you just take the force, break it up into components, and now we add them together. Well, my horizontal components are going to cancel each other out, which is good because I know the thing's not going to accelerate left or right. So my total force is 2 times that should be Ft. 2 Ft sine phi is acting down. That's my total force acting on it, downwards. And just for the sake of ease, we'll just say down is positive. So that force there, that net force is acting towards the center of this circle here. What kind of force is that acts towards the center of a circle?
There's a word for it, I can't think of it.
I heard the last part where you couldn't think of it. That sounded like you almost said it the first part.
No, I said, there's a word for it.
Okay. What is that word?
It's not centrifugal force, is it?
Wait, which one did you say?
Centrifugal.
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 No, the other one.
Centrifugal.
That's the one. Newton's second law tells me force equals mass times acceleration. There's my total force acting on it. That should be equal to that mass of whatever size I'm picking times centripetal acceleration. And the formula for centripetal acceleration, or centripetal, I was hoping B squared over R. I hope that rings a bell. So R is basically the distance from the center to my bit of rope. Now, the way I've drawn it right here, I've taken a much larger section of mass here. What I really only care about is that I want to get this as small as possible in this region right here. So I'm basically gonna let my angle phi go to 0. I'm not letting it be 0, I'm just getting closer to 0. Mathematically, we would write the limit as phi goes to 0. Now, there are a lot of times where you go, oh, I'm just gonna let phi equal 0 and I'm good. But there are other times where if you do that, you end up with something that's, well, if we let phi be 0, then sine of 0 is 0. This whole thing becomes 0 and
You got
the acceleration 0 again. So we're just gonna get as close to 0 as we can, but never actually make it 0. In other words, we're gonna let phi be incredibly tiny. What is this roughly equal to if it's incredibly tiny?
1, 0.
0.001.
I know we come.
Pi.
Small angle approximation?
Radian,
What'd you say?
radian. It's,
Oh, if it's in radians, that part of the small angle approximation, but if phi is small and in radians, what is sine of phi approximately equal to?
isn't it 1?
Not
radian?
1.
57.29 degrees.
That's 1 radian. I'm looking at for sine of phi. If phi is much less than 1,
No, it's equal to itself. Sine of pi, or
phi,
phi is roughly equal to tan of phi, which is equal to phi.
yeah. That's the part that I wanted. So my equation there has now been reduced down to, that's right, we did it when we dumped the simple pendulum. So 2 times whatever my tension is times phi is equal to mv squared over r. All right, so let's see if we can get it down a little bit farther. If I have a circle here with some radius r and some angle theta and some arc length here, which I'll just call s, what's the relationship between s, r, and theta? If theta's in radians. We talked about this one also in the past.
Radius is gonna be half of the diameter.
Okay, that's true.
So,
The radius times the angle equals S.
There we go. The arc length is equal to the radius times the angle, assuming the angle's in radians. So if I look at this bit right here, my length here, that length has got to be equal to r times my angle, which is 2 phi.
What is that?
What is this? That I'm using this formula right here and applying it to my little wedge here. It
No,
just,
what is that letter? What is that?
L,
L?
Oh, it's just L?
L.
Okay.
Yeah, I put the curl in there to differentiate it from my ones. Yeah, I suspect only one of you has had potentially experience with this, of typewriters without the number 1 on it. I don't know if you ever dealt with that. The typewriter we had growing up had no 1. You're supposed to use the letter L.
L.
All right, so we have this other relationship and we need one more bit and we are good to go. And that is, introduce something else, and this is known as the linear density.
Micro.
Using the letter mu. This is the letter mu. Lambda is often used for linear density as well, and so if you're looking at some of the stuff, you might see a lambda there for linear density. Obviously, lambda is also being used for wavelength, so really don't want to use that for linear density also. So, before we define linear density, what is density? What's the formula for density?
Kilograms per cubic meter?
All right, that would be the units. So kilograms is a unit of,
Mass.
and cubic meters,
Area. Oh, volume, sorry.
volume. So density, normal density, regular old density is just mass over volume. Surface density. So this is just normal density, sometimes referred to as volume density, but if someone just says density, this is the one they're talking about. Surface density. Would be, surface density would be mass over what? We're talking about a surface now.
Would that be area?
Yep, so mass over area. So that would be kilograms per square meter. And then linear density, we're now dealing with the density along a line. Mass over,
Diameter?
not diameter,
Length?
yes, that one. We assume the diameter is small. So we got mass over length here. Or the mass of something that has a uniform linear density would just be multiply both sides by L, the linear density times the length. We now have all the pieces. Let's put them together. Let's see, let's get rid of that. And that. So I have 2 ft times phi, and from this equation right here, I have phi would be the length over 2 times the radius, or the diameter. That's equal to mv squared over r. Well, m is just going to be mu times our length there of L, v squared over r. Let's cancel stuff. My r cancels out. The 2's cancel out. My L cancels out. And I am left with a much simplified, the tension is equal to my linear density times my speed squared. Ultimately, I want to solve for v here, so I'm going to get rid of the mu by taking this over, so I have tension divided by mu is equal to v squared, or the speed of this wave is equal to the square root of the tension over the linear density. So if I have anything that's traveling along a long, thin line, this is the formula. But I also have the advantage of the fact that speed is also, if I have periodic motion, if I have some wave being created again and again, that's also equal to the frequency times the wavelength. So if I know the linear density of a piece of string, for example, and I know the tension, if I can measure the wavelength, I can figure out the frequency. Or, pick a different unknown. So I say, let's demonstrate it. You need to stretch your legs or something, now would be the time to do it as I'm setting this up. You stand. Another one.